In this example, we're asked to graph a transformed sine function and then to find when that function equals 0. I'll give you a few seconds to have a look at the problem. Notice we're asked to graph and to find solutions on the domain 0 to 2 pi. And that domain is the domain for the transformed function. So it's not about x being between 0 and 2 pi, but graphing this expression here between 0 and 2 pi. So here's the approach we're going to take for graphing. We're going to look at the domain and range of a normal sine x without any transformation, and then we're going to look at the transformed sine x, and we're going to see how the domain and range changes, and we're going to see how many cycles that we need to draw for the given domain. So we start off with a standard sine x function and how we would graph that sine x for one cycle between 0 and 2 pi. Sine of 0 is 0, sine of pi on 2 is 1, and so on, 3 pi on 2 minus 1. So we're going to look at how that sine function changes under the transformation, and to get our equivalent x values, we're going to ignore the vertical transformations, and we're going to look at the equivalent, or we're going to look at how x behaves under the transformation. So if I define f dash of x as sine of 3x minus pi on 3, that comes from here, then I've used the horizontal transformations but ignored the vertical transformations. Then to find how these x values change under the transformation, I want to make f dash of x dash, the new x values, the same as f of x. So remember that f dash is sine of 3 of x minus pi on 3, that's f dash of x. So f dash of x dash, sine of 3 x dash minus pi on 3, I want that to equal sine of x. So just equating the contents of the sine function, I want 3 x dash minus pi on 3 to equal x. And that gives me the relationship between my transformed x dash, and my original x. I can just make x dash the subject, and x dash equals x on 3 plus pi on 3. And now I can look at the x values for one complete cycle of my transformed sine function. So applying those transformations, if I start with x equals 0, 0 on 3 plus pi on 3 is pi on 3. If I go x equals pi on 2 divided by 3 is pi on 6 plus pi on 3, and so on for pi on 3 plus pi on 3, and then for 3 pi on 2, if you do the calculation, that gives you 5 pi on 6 when you divide by 3 and add pi on 3, and 2 pi transforms to pi. So writing those out, and just to make those changes in x values easier to see, I've written them all as a fraction of 6 rather than simplify the fractions. So we've got 2 pi on 6, 3 pi on 6, and so on up to pi, 6 pi on 6. So that's my transformed single cycle of sine x. And now we're going to look at put back in the vertical transformations when we calculate the value of that transformed sine function. So 2 sine of 3x minus pi on 3 plus 1 for 2 pi on 6 gives sine of pi minus 2 pi on 6 minus pi on 3 is 0. Sine of 0, 2 sine of 0 is 0 plus 1. So our first y value is 1. And substituting successive x values into our formula gives the y values 1, 3, 1, and so on. And we could have got these values directly from the y values of the sine x function, the standard sine x function. So if we look at those vertical transformations, we're multiplying by 2 and adding 1, 0, multiply by 2 and add 1. 1 times 2 is 2, add 1 gives us 3, and so on. 2 times minus 1 minus 2, add 1 is minus 1. So there's our transformed sine function. We can graph that for one cycle. How many cycles are we going to be graphing for this domain 0 to 2 pi? Well, looking at our horizontal dilation 3, our period for a sine function is 2 pi divided by that horizontal dilation 2 pi on 3. And that period is the horizontal length of one cycle. And so the number of cycles, the domain, the length of the domain, 2 pi divided by the horizontal length of one cycle, 2 pi on 3, gives us, we just flip that and multiply, simplify and multiply gives us 3. There are 3 complete cycles. So we can go ahead and mark the graph and draw in that first complete cycle of the transformed function. So I've written in here the domain for 0 to 2 pi, and we've marked those as pi on 3, 2 pi on 3, and so on up to 6 pi on 3. And we've marked in the range so we can go ahead and plot our transformed cycle. And the first point we'll put in is that pi on 3, 1. And we'll continue with the other points. So we've got 3 pi on 6, which is pi on 2, 3. We've got 4 pi on 6, 2 pi on 3, maps to 1, and so on, minus 1 and 1. And we can draw in that curve. So there we have one cycle, roughly drawn in, and we now need to extend that for the entire of the domain that we want to draw. So we can just simply by observation repeat the points going right and going left, or we could extend our table and calculate the other x values on the domain. So to extend the end of the cycle, I look at the start of the cycle and I go one step. So my first step, I go up to 3. For my next step, I go back down to 1 and so on, minus 1. And I extend that cycle and I can keep going by looking back at the cycle. And similarly this way, I can look at coming back from the end of the cycle and then I can extend to the required limit of the domain. So I've gone and drawn that in, taking it up to the limit of the domain, 6 pi on 3 or 2 pi. And coming back to the question, how many solutions to that transformed function equals 0 on the 0 to 2 pi? And we've got 1, 2, 3, 4, 5, 6 solutions. 6 solutions. 6 solutions, and that shouldn't surprise if we've got 3 cycles and we've got potentially 2 solutions each cycle, then we would expect a total of 6 solutions. If the value we'd chosen was 3, then there wouldn't be 2 solutions for each cycle, in which case we'd only have 3 solutions, 1 solution for each cycle.